Hi, and welcome to the RIP channel. In this video, we'll look at the Laplace transform of the nth derivative of f as done by Horowitz. Take a look at the description if you want to see a link to Horowitz's paper. We're going to use RIP, or row integration by parts, which is the tabular method for integration by parts, with an emphasis on the rows. Each row represents an integral, and we proceed one row at a time. If you haven't yet seen an introduction to RIP, take a look at the motivation and process video before you follow up with this one. Under suitable conditions, the Laplace transform of the nth derivative of a given function f is given by this integral transform where we introduce a new parameter s in e to the minus st times that nth derivative of f and take the improper integral from 0 to infinity with respect to t. What it gives us is a polynomial in the new variable s where the coefficients are given by the derivatives of f evaluated at 0, paired with a remainder that's the Laplace transform of the original function f times s to the n. This formula follows immediately from RIP. And to find a formula for the antiderivative, RIP yields the following. Start with plus sign indicating a positive 1, differentiate e to the minus st, that will kick out the successive powers of s that we see in the formula. Integrating the nth derivative of f will eventually yield the original function f through enough iterations. First iteration, we alternate plus minus signs. Differentiating e to the minus st, a negative s kicks out according to the chain rule, where we're treating s as a constant and differentiating with respect to t. And of course, an integral yields the n minus first derivative of f in the second row. Next row down, alternate plus minus signs, another power of negative s in this case, so it's negative s squared here, times e to the minus st, another integral. Proceeding accordingly, to track how we get this information in this row, let's take a look at what happened in the integral column here. Well, if we integrate the nth derivative of f n minus 1 times, we get to the first derivative of f, and correspondingly taking n minus 1 iterations of plus minus signs, as well as derivatives of e to the minus st, yields these terms. So notice that we have negative 1 to the n minus 1 from the alternating plus minus signs, as well as negative 1 to the n minus 1 coming from the successive powers of negative s coming out of the chain rule here. One more row down, we have one more power of negative 1, one more power of negative s, and of course, just the original function f. When we take the product of everything in this bottom row and integrate that product, it gives us the antiderivative for the Laplace transform of the original function f times s to the n. So before we take the integral from 0 to infinity, of course, we need to gather the terms, and we do that as follows. The first term is obtained by 1 times e to the minus st going down a row, multiplying by the corresponding n minus 1 derivative of f. Next term, negative 1 times negative s, gets those negatives to cancel. Going down a row, we pick up s times e to the minus st times the n minus 2 derivative of f, so on and so forth. And in the second to last row, we pair it with the very last term from the integral column to get s to the n minus 1 e to the minus st times f of t, where the powers of negative 1 have canceled themselves out. And the bottom row, once we take the product of all these terms and integrate it, yields the last term from integration by parts. So of course all that's left to do is to evaluate everything in these expressions here from 0 to infinity. So, assuming the terms vanish accordingly at infinity, what that means is basically that we need the derivatives of f to be of exponential order, yields the following. Okay, so we take the antiderivative portion from RIP in blue here, evaluate from 0 to infinity, and then tack on the integral that we had from the last row of RIP. And notice that this will be the Laplace transform of f. But that's getting ahead of things a little bit. Let's see, if we evaluate at infinity, or in other words, let t tend to infinity and investigate the limit, well, by having the derivatives of f be of exponential order, and for the right types of variables s here, those terms actually kill off, and the only things that we're left with are the derivatives of f evaluated at 0. The exponentials where t is evaluated at 0 become 1s. And so here we go. We have a polynomial in S with coefficients given by derivatives of f evaluated at 0. And as I said before, s to the n times the Laplace transform of f is exactly represented by this integral here times s to the n. And that's it. So, please subscribe, check out the playlist, and learn to master integration by parts.